All right, so when we're drawing these Lewis structures, we're drawing a bunch of lines, some dots, and some letters, right? So what does this mean? Is this just some kind of random picture? Obviously not, right? This is just a representation of very complex, three-dimensional interactions between elements and their electrons. Right, so even though it looks like a relatively simple drawing, it's actually representing something that is actually quite complex. So let's think back to general chemistry. Remember that electrons stay in orbitals, right? So the orbitals are kind of the houses of the electrons. They're the region of space occupied by an electron. Right, you kind of think of this as the house for the electron. And remember that there's 2 electrons per orbital. And so if we take a look at our handy dandy periodic table here, we know it's also organized based on these orbitals. And so this 2 groups over here, this 2 column is called the S block, because it has the s orbitals in it. And then this grouping of 6 groups over here is what's known as the p block, because there are p orbitals. And so we can see in one row, in one period, we have 8 valence electrons, or we have a certain number of orbitals, right? So per n, in our lone atoms, we have 1 s orbital and then 3 p orbitals, right? 1 s orbital contains 2 electrons, and then we have 3 p orbitals for 6 electrons. Remember, in organic chemistry, we more or less just ignore the transition metals. And so if we think about what our s and p orbitals look like, remember that the s orbital is a sphere, right? And it can contain 2 electrons. And then we have 3 different p orbitals. They all look like dumbbells, just in different orientations, right? So one's a dumbbell kind of going up and down. The other is the dumbbell going left and right. And then finally, we have a dumbbell where one lobe is going outside of the board and one lobe is going inside of the board. And so that's when an atom is by itself, it goes into these orbitals. When atoms interact with one another, their orbitals overlap. And it's this overlap of filled orbitals that create bonds, right? So in our Lewis depiction, what we show is 2 hydrogens with 1 dot each. In kind of the real life scenario, what we have here is a hydrogen with its 1s orbital and an electron in it, and then another hydrogen with its 1s orbital and another electron in it. And then in the Lewis structure, we draw a straight line to indicate this bond. But really what's happening in real life is this overlap of electron density and this sharing of bonds. And so you can see how these 2 round orbitals would form this bond. And so while using atomic orbitals works for H2, it doesn't work for many other compounds. So if, for example, we think about carbon, carbon has 4 valence electrons. It has 2s2, 2p2, right? So its 2s orbital is filled. And then it has, of course, 3 p orbitals. So one going up and down, one going left and right, and then one kind of going in the back of the board with the other lobe going in front of the lobe, right? And we put 1 electron in one each of these orbitals. And then when this interacts with hydrogen, what you would expect is to just have two interactions, right? So we can fill these orbitals, right? And so what you'd predict that if you combine carbon and hydrogen, you might predict that you'll form CH2 at a 90-degree angle. And that's not true, right? This is not how CH2 exists, right? So just using atomic orbitals, is not sufficient to describe the bonding between carbon and hydrogen. What we know that carbon forms 4 bonds with hydrogen, and that it forms a tetrahedral shape, right? So this wedge over here means that this hydrogen is coming out of the board, and then the dashes back here mean that that hydrogen is going back into the plane of the board, right? So we know that it's 4 bonds, and that has a tetrahedral shape. And so how do we explain this? Well, it actually gets quite complicated, so we'll just kind of give the short explanation. Remember that electrons are actually waves, and waves mix with one another, or they interfere with one another. So for example, if you had 2 waves, something like this upper wave, I'll show the kind of the stuff going above the line as orange and below as purple, right? If you were to combine these 2 waves, they would constructively interfere, right? And form this bigger wave. And vice versa, if your waves were out of phase, something like this wave, they would deconstructively interfere, and they would essentially destroy one another, and there would be no wave at the end. And so that's the same thing that happens to our orbitals. Our orbitals mix, and we call this hybridization, or that they hybridize, right? So for example, if you have this 2s orbital, right, and one of your 2p orbitals, right, the 2 lobes are in different phases, and so we can have different types of mixing, some of it constructive, some of it deconstructive, right? So this isn't actually totally correct, right? But we'll say that this part is kind of constructive, this part is destructive, and so what kind of orbital you might imagine is something like this. We'll see when we talk about sp orbitals, actually gets a little bit more complicated. But overall, what we're seeing is that our orbitals in a lone atom are not the same as the orbitals in a bonded atom. The exception to this is that single bonded terminal atoms don't hybridize. An example of this is hydrogen, right? So if you have this hydrogen connected to this carbon, this hydrogen is not hybridized. And so we'll take a look at the different hybridizations coming up.